Einstein's general relativity assumes the geometry of spacetime is completely determined by a metric-compatible connection. But what if we break that assumption? What if the connection between nearby points in spacetime carries information independent of the metric itself? The authors generalize the Palatini approach by treating the affine connection as a variable independent of the metric. This introduces two new geometric quantities: nonmetricity, which measures failure of metric compatibility, and torsion, which captures antisymmetric transport. Together they encode richer geometric structure than general relativity allows. How do these new geometric objects actually enter the theory? The Lagrangian combines scalar invariance of curvature, nonmetricity, and torsion. Crucially, when the authors derive field equations, they find the connection has no kinetic terms. This means nonmetricity and torsion are not independent dynamical fields. They're algebraically determined by the matter content and the metric. The connection equations can be solved explicitly to express nonmetricity and torsion in terms of matter fields and their derivatives. Matter with hypermomentum, like spinning fluids or dilatation currents, sources these geometric structures. When substituted back into Einstein's equations, they modify how matter couples to geometry. What does this algebraic role mean physically? Because nonmetricity and torsion respond to matter's internal structure, its spin, dilation, and shear, they provide new channels for matter to influence spacetime. These effects appear as corrections to Einstein's theory. The authors note that while second-order theories keep these quantities auxiliary, higher-order Lagrangians might liberate them as true dynamical fields. In the theories examined here, nonmetricity and torsion remain algebraically constrained. But the framework opens questions about what happens when you relax those constraints, whether through higher-order Lagrangians or special matter couplings. The authors suggest investigating how these extra degrees of freedom behave when excited, and what observable consequences might emerge at accessible energy scales. Time that is a long time effect. The authors demonstrate that nonmetricity and torsion enrich the geometric language of gravity, but in second-order theories they serve as intermediaries rather than independent actors. They translate matter's hypermomentum into geometric effects, modifying how fields experience spacetime. The real dynamical story may emerge only when we venture beyond second order. Metric-affine theories reveal that spacetime geometry has more expressive power than Einstein imagined, even when that power remains latent, encoded in algebraic relations rather than wave equations. To explore more cutting-edge research in theoretical physics, visit emergentmind.com.